Today's my presentation will be about CHSH inequality. I think most of you guys are familiar with this, but I just wanted to little bit more investigate about this. So it's very easy, so please enjoy. Okay, so I'll try to introduce CHSH. So it stands for scientists name. So I think everybody knows that. So CHSH game, there are two players and they are cooperating players, and there is one referee, and two players are far away. And the referee will give A and B, which is beat, to the both players, and they give back X and Y. So this is the chart of the how to get the points. So in order to win, they should get as many points following this rule. So first strategy will be the zero strategy. The zero strategy gives always zero back. And then what happens is that it will get points for the first three cases, but it will not get for last one. So it is 75% of winning. The next strategy is A strategy, which is for the first player. He will give back what he get. So the input and output will be same for the first player. And for this case, the bottom player maintains the zero strategy. So in this case, also a 75%. So next strategy, it is 1 minus A strategy, which is the first player will just flip. For this also we get 75%. So we can think that for deterministic strategy, we have 4 types of strategy each classical player can choose. So the deterministic strategy always gives the maximum of 75%. Oh, yeah. Yes.
I'm sorry, but I can't understand this. The rule game. So
Yeah.
referee gives random number to.
Yes. Referee gives a random number to each player. Yeah.
And both players have to give a number.
Yes.
What they choose.
Yes.
0 or 1.
By their strategy. Yes.
So, and the point if the X is the number what A give.
Yes.
And Y the point B if B give. And if X equal to Y.
Yes.
Can A get a point
in
this chart?
So the chart is always same for all the strategy.
Yes.
And each player can choose 0, 1, A, or 1 minus A strategy. And it's same for the bottom player. So yeah.
Each player can choose 0, 1, B, and 1 minus B. Yeah,
B means what he gets. He outputs what he gets. So the input and output is same. And 1 minus B means it's flipped. So if he gets 0, he will give 1. And if he gets 1, he will give back 0.
If you think about just last strategy, just result, if player 1A, player A gives 1, and player B gives 1.
Oh, A and B is input. X and Y are
저만 이해를
output.
못한다.
네.
오케이. 이게 되게 사실 되게 생각보다 복잡하잖아요. 이게 한번 봐서는 솔직히 저도 이해가 안 가더라고요.
저는 이 게임은 처음 봐요.
어,
CSH는 아는데 게임은 처음 봐요.
okay. So actually, this is a really well organized example, I think. So you can understand. So 그러니까 I'll explain in Korean. 그러니까 심판이 A랑 B를 랜덤하게 앨리스랑 밥한테 줄 거잖아요.
A랑 B는 숫자예요.
그쵸,
숫자죠?
실자예요.
좋아요.
0 또는 1. 그래서 이제 0 또는 1을 앨리스한테 줄 거고 0 또는 1을 밥한테 줄 거예요.
좋아요.
그러니까 요거 사이엔 아무 관계 없어요. 그리고 이제 얘가 이제 뱉을 거잖아요. 받았으니까. 그래서 비트를 심판한테 줄 거예요.
네.
그래서 근데 심판한테 줄 때 스트래테지를 4가지 중에 하나를 쓰는 거예요.
그렇죠?
항상 0을 뱉는 거, 항상 1, 4가지 스트래테지 이해되시는 것 같고요.
네.
네, 그래서 X랑 Y가 만약에 A랑 B는 인풋이에요. 인풋이 만약에 0이랑 0이었다.
네.
그런 확률은 이제 25%겠죠. 그러면은 이제 그 경우에는 그 점수를 얻는 기준이 그 아웃풋이 X랑 Y가 같아야 되는 거예요.
그러니까 둘이 같이 얻는 거예요?
그렇죠. 둘은 한 팀이에요. Yes, they are cooperating.
정수의
네.
딜레마 생각했어요.
Okay. Actually, it's really nice to understand. Yeah, it's good question. It was good question. Yes.
둘이
예.
싸우는 줄 알았어요.
예.
그래,
Yeah.
맞네.
Yeah.
그렇지.
Yeah. So for this deterministic strategy, the maximum will be 75%. I think it's everyone is clear. Huh? Now let's move on. So can we use some better strategy that can be bigger than 75%? So we use probabilistic strategy. So now player will have a dice. This dice gives a 4-sided dice. So it will help the player to choose which strategy among those 4 deterministic strategy, what will the player choose? Okay. So each player has the dice, so they can choose 0, 1, A, or 1 minus A. Okay. So as you can easily guess, this also cannot exceed 75%. So for example, if they have 1, 1 for their dice, then okay. So my point is whatever you choose, the probabilistic strategy actually includes the deterministic strategy. So it always have 75% as well. Yes. Yeah. So the probabilistic strategy also gives 75%. Is it clear? Okay. So even though for all types of dice, they will always get at least one might be failed. So the probabilistic strategy is 75. Actually, these are all strategy for classical players. So if you think about it, the combination of those deterministic strategy are just it contains all classical strategy. So actually we had tried everything for classical. So even for like something like this kind of coin strategy, whatever you think of, if you add a coin like this, and then you have this type of chart, But even with this, if you calculate, you will only get 75%. Okay, so now let's move on to the quantum version. So now the player has the entangled spins. Okay, so with the given theta, this will give 1, and this probability it will get 0. So if two players measurement is 180 apart, we can always get the point. Okay, I'll explain this. So what means entangled? When this is up, this will always give down, right? And so the quantum strategy always gives this kind of probability. We can explain this with this model. It can be a little confusing, but the referee is giving A and B, right? And then the player will choose the 0 or 1 direction. It is the measurement direction, depending on the input A he gets.
Oh, A and
Yeah.
B is entangled state.
Oh, A and B has entangled states. Yeah, they are entangled, and it is just the measurement direction. And also it is same for the player, the bottom player, and then he will get, and then depending on that, he will choose 0 direction or 1 direction. So I forgot the arrows, but please imagine. And so if you calculate, you will get this value. So actually you will get always this value. That is important. This is not, this is also maximal, but it always gives this value. Whatever the referee gives A or B, it will always gives this value. I think you can calculate by yourself. It is just calculation with this thing. So I'll just,
The theta is
yeah.
random.
Yes, theta is this angle. It will be the from the origin. It will gives its theta. It means the rotated axis to the measurement axis. Yeah. Yeah. Please calculate. It's very interesting because it always gives this value. Yeah, very interesting. And okay, and I'll move on to the hidden variable theory. With this simple model, we can also explain that local realism is falsified. So it is wrong. Actually, until here, we cannot say which is wrong or right between the quantum entanglement, which is spooky action in the distance, or local realism. So which one is right? We don't know yet. But we can say that hidden variable theory gives different value with the spooky action in distance. So with the entanglement spin experiment. So they are not the same. And actually hidden variable theory gives the same result with the classical theory. So hidden variable theory doesn't think that spin is no, we already know the spin's value. So we already know where the spin axis will be. So we just define it. And so we can say that it has deterministic measurement. And as you can see, the player, above player and bottom player has different direction of measurement each time. So if the referee gives, let's say the referee gave above layer 0. Then this 0 value, and it will calculate in this direction. And the bottom player will have the bottom direction of measurement. And then it will be actually the same for the classical theory. I could not really draw this. Yes, so actually it's same with the deterministic strategy.
So it's a bit confusing to see the difference between
Yes.
what
Yes. Actually, maybe I should draw.
Oh, yeah, you can draw, but
Yeah.
turn the camera to.
Yeah, okay. I think you can see. I'm sorry. So, so deterministic, no, the hidden variable theory thinks that 0, 1, 1, 0. So if the referee gives, let's say, Alice and Bob, and gives Alice A0, okay, then it will have a measurement direction at this way. So from here, let's say it's here, then the bar will have a different measurement direction this way, and then
Alice and Bob cannot interact each other.
yes, Alice and Bob cannot interact each other, but it's a good question. Before getting this A and B, they can interact.
And
Yes.
choosing a setup.
Yes, they can choose them. So that's how it is. Right? So now, since he got the value of no interaction anymore, and Alice gave 0, and there will be some kind of a spin. Let's say it's here. Then it will have the opposite direction for here, right? Because they are entangled. Right? So different direction. Yeah. So it will measure here, and then this is theta. And for here, this will be theta. And then
아까 했던 거랑 비슷한 얘기인 것 같은데. 그러니까 점수를 얻는 기준이
네. 점수를 얻는 기준이 이걸 만족해야.
양 기준 다요?
그러니까 요걸 받았을 때는 이걸 만족하면 점수로 돼. 네.
네.
So let's say they got 0 and 0. Then if they got this one and this one, and they will have measurement from this one and this side.
If A and B is intended cubic,
Yes.
how can decide the A and B value?
Oh, A and B is from the referee. So for this, this is for referee.
Where is intended cubic?
Oh, these are intended. Sorry.
I'm sorry. I understand. I just understood A and B are intended cubic.
Yes. So this one and this one, and it will measure in this direction and this direction. So as I mentioned here, with given setup, this gives 1 and this gives 0. So for here, it will get 0 for this probability and 0 for this probability, and you need to calculate and sum all of them to get it to see if this is satisfied.
Now A and B, the reference angle is just rotated about how many?
The reference angle
Yes.
will be just here.
Oh, and B's reference angle is here. Is at 0 and 1 position is different with A.
Yes.
Can I understand?
So the measurement basis is different, but the
Measurement basis is different.
basically
Yes.
measurement basis is local.
Yes.
And if you're considering a quantum version, 2 qubits are entangled, so it's non-local. But in this hidden variable theory, although it's correlated, they're not entangled, so it's local.
Oh yeah, yes. This can be an explanation. Thank you. And that was what I wanted to explain. So because of the hidden variable theory, it becomes local. So it is same as the deterministic version. Yeah, we're probably yeah.
I think the entanglement and classical theory, the difference between entanglement and classical theory is the entangled qubit has and measurement by 2 different layers. If entangled qubit is measured by 2 different layers, and they can get different value. It's the entanglement, okay?
Yes.
In classical theory, there is same, but 0 and 1 bits, not qubits, and mixing them, and they cannot see what is the bit, and they choose randomly. It is classical theory. I think the determinant theory just says what I'm saying. Is classical beats, I think, because they can choose beats just classically, but deterministically. But in entangled qubit, they cannot. This is not determined. This is just entangled. After they
yes,
before
yeah, we can just think it's not entangled. It's local because if the measurement is choose, then it has some kind of relation. So if you do, you'll get same. Okay, yeah, so last part, there is no signaling theorem, and this can also introduce with this kind of machine, which gives for the bottom player, it always gives 0 value. Okay, and then the above player, it acts like an AND gate. So if both, this is a lever, and if it gives same, if it's only 1 1, it will show 1. Otherwise, it will just show 0. And this is the output. So this will be X and Y. So using the same chart as before, we can check that the players can always win. So this is not following the physical law, because the communication is allowed, which is because it is faster than light, it's always winning. So this setting shows that this is not possible. Yeah, so the nature has no locality. Yes. So these are some questions about CHSH. Actually, it's a kind of a Bell inequality. So this question is from the Nicholas Giseng's archive, and he wrote that why is CHSH is the most efficient way to prove no local state? It seems to be that CHSH is really nice inequality to prove that whether one state is no local or not, but it is not proven. So it's an open question, and yes, there are actually very many open questions. Oh, look. And this is I wrote because I am currently studying about the loopholes. And I am studying about the loopholes that can occur in the EPR problem. So in order to show that EPR is wrong, we need to first close 2 loopholes, which is locality loophole and detection loophole. This is related to experimental physics, but it is important to find such Bell inequality that closes the locality loophole and detection loophole. So that is my question, and thank you for listening. Yeah. Oh, yes.
Can I get a reference about this?
Okay.
Okay.
Yes, yes. Yes, thank you. 이거 나가면 되나요?
아니요.
아,
질문.
yeah. Do you have question?
Thank you for the presentation, Yunjung. It was very nice presentation, and I was just wondering. I was just wondering, could you explain more about the loopholes you just mentioned?
Okay. Yes. Thank you for it. Question and okay. Actually, loophole is already mentioned in the paper of CHSH. So the authors already predicted that there will be some problems when showing that CHSH is really if it's satisfied in the real nature. So, okay. So actually detection loophole is something about the efficiency that is needed to, so there are probability that we can measure correctly or not. And the detection efficiency for now, it needs to exceed at least 85%, 80%. But if we use more entangled state, we can actually lower the efficiency of the detection efficiency. It is not proof, but it might be. So I am trying to find a Bell inequality that needs less detection efficiency.
Aren't we already using maximally entangled states for CHS as inequality?
Okay. Oh. Oh, yeah. Yeah, I think I'm not sure about I think I need to study more about the detection loop. 네. 네네. 네. 네네.
디텍션 이피션시가
네.
81을 넘어야지
네네.
CHSH를 만족하지 않는 게
네네.
그게 진짜라고 말할 수 있다.
그쵸. 네. 맞습니다. 네. 그러니까 지금 이제 레퍼런스 논문인데 제가 기억이 잘 안 나가지고. 네, 그렇습니다. 어쨌든 그렇고, locality loophole can be closed if they are actually not giving any interaction to other so the Alice and Bob need to be far apart. So they are not interacting. So that is something about the locality loop. Yes. So for real experiments, there might be interaction, but locality loop means it needs to be far apart. Yes.
So conceptually, it's okay, right?
Yeah. Conceptually, it's fine, but for real experiment, I think the more bigger problem will be something about the detection loophole. Yes. Yeah, thank you. Do you have any more questions?